talk in a more detailed way about high-frequency electronics behind what we talked about on Tuesday, right? We said high-frequency broadband measurements or technologies could have some potentials there in the so-called NAB-on-chip development, okay? Then today, I think in the beginning, I would like to show you a few more examples about why we need high frequencies, right? And after that, we will discuss about a few specific characteristics of high frequency signals or circuits or electronics in general, right? In particular, we will talk about the transmission lines, which look very simple. Actually, they are kind of difficult if you deal with it in detail. And then we will discuss about something called scattering parameters. That is the kind of parameter unique to high-frequency electronics. Okay, it's a kind of special language there. Okay, and there we will then discuss something called dispersion. And for optical people, you know dispersion. Yeah, actually in high frequency, we have that dispersion issue as well. At the end, then we will go through the basic building blocks, or not blocks, components for you to use to build high frequency circuits and systems, okay? Like some general properties or figure of merits for transistors and some passive components. Okay, we saw this. Yeah, some more examples about where we need to use high frequency electronics or high frequency kind of domain in general. We all know these things, right? I can't drive without this GPS. You need high frequency stuff. Everyone needs a phone, right? Yeah, everyone needs a Wi-Fi connected laptop, and I don't know if it's there already or not. For the shopping cart, you put a small gadget there. The idea is if you pick something from the shelf, it will be automatically registered. Then you don't have to wait at the checkout line, right? But if you don't like it and put it back, then it will subtract out, right? That will be good. So Walmart, for example, can save manpower. They don't have to have so many cashiers there, right? That's good. Yeah, we saw this, that like a cellular base station, and we need high frequency there. And GPS satellites, yes, communication, high frequency. Smart homes. This was many years ago, actually, started by Intel. The guy, Moore's Law. Targeting seniors, so they can have a comfortable life in their own homes at the same time, at an affordable way, right? You don't have to hire expensive people to take care of them. That's very expensive. And recently, you know that there was some Apple plans. Apple is getting into smart home business as well. I think this was there was some report a few days ago. Okay, Apple, a big move into smart home. And once again, the idea there is you have maybe a computer to control everything you need inside your home or around your home. So that was also part of previously discussed like energy or power control using wireless techniques. So that's high frequency. Okay. So in this smart home, you definitely need a wireless or high frequency techniques or electronics there, right? We know this, Google, right? Driverless cars. You need a lot of wireless sensors, control systems. So they are definitely high frequency related. And such as radar, yeah, you could use some light as well, like optics there, right? That is for the consumer products. We know this. For the scientific exploration and DoD application, military application, all these things need high frequency electronics. And the drones, right? They need you to tell where, when to fly to where, right? And how do you do that? Through high frequency electronics, okay? And this one. Yeah, high frequency electronics is very important. It's everywhere. Then what is high frequency? Okay, so if you look at the spectrum from DC all the way to cosmic ray, right? And people actually often say radio frequency, which is from about 3 kilohertz all the way to 300 gigahertz. And within this radio frequency spectrum, you have different bands, like a microwave. Here it shows from 100 megahertz to 300 gigahertz, okay? And sometimes people say it's from 300 megahertz to 300 gigahertz. There is some discrepancy. And yeah, it depends upon your application or depends upon what you are dealing with. High frequency may mean somewhat different things, okay? But often we will see later, when we see high frequency, we mean when your wavelength of your signal is comparable with your circuit size. Comparable means within a factor of 10. Then you have to deal with your circuits, like in the context of high frequency or a region, okay? And there is 2 points I want to communicate with you, which is, the first one is the spectrum is very expensive, actually, because it's the resource, right? If I'm using this frequency point to do something, or this frequency range, other people can't use it. We can't make a separate one. So an example here, let's say, is that's in India even. This was 2 years ago, 3 years ago. They reserved a price for CDMA spectrum, just 5 megahertz. It was $1.7 billion for the right to use that 5 megahertz spectrum. It's very expensive. That was why when a professor, I think at Cornell, he invented this CDMA code. What is that? You can reuse some spectrums. Okay, that was licensed at a very high price, so he disappeared from Cornell. Other people said, why did he need to work anymore? Because he had plenty of money. He invented that CDMA technique because it's very expensive spectrum-wise. Okay, that's one point. Number one. Point number two is you will see later from the device development. And point number two, from 300 gigahertz to about 10 terahertz. That range is called terahertz frequency. Okay. And the terahertz frequency, people like to say we have a gap there. We have a gap because it's difficult, that frequency domain to handle. The main reason is the source. Okay. I think I'm not sure if Dr. Harrow had a chance to tell you guys how high the transistors could work, right? And in this frequency range, the frequency is very high for the transistors to generate power effectively. but it's also too low for the optical people. So the energy level is not that distinct from, let's say, close to the thermal energy, right? So it's difficult for the optical people to handle. So it falls in the in between. And this is a very active research area as well, okay? Now, behind all those systems we talked about, and if you look hard, open those systems, and you can find a typical, a basic kind of circuit module would be this transceiver. It is, as long as you understand how to design this transceiver, pretty much you can understand how to build those systems reasonably well, okay? And this is a multi-technology transceiver block diagram. And the problem associated with this circuit when you want to design that is that very often, okay, the frequency you are dealing with is very high. I just mentioned that. So the wavelength of your signal is comparable with your dimensions, with your circuit or device, even device dimensions, okay? And because of that, you can't use the traditional like DC circuit concept, right, to design your circuit. Then here's an example I show you. Like if you have a 1 millimeter long wire, 1 millimeter is not very long, and the rule of thumb is its inductance is about 1 nanohenry. If you are dealing with a circuit or signal at 1 megahertz, it's okay. You calculate the impedance, right? J omega L. That gives you 0.0062 ohm. You can ignore that, right? That's very small. But if you work at 1 gigahertz, it's a 6.2 ohm already. It's noticeable at least, right? And if you work at 10 gigahertz, which is not a very high frequency, it's a 62 ohm. That's very high. That will spoil your design, your DC design. Okay, so you have to consider those length-related effects or issues. So then you can look at those collections or collectors, and they are of their own category called transmission lines, right, or waveguides. For longer distance or higher power, people still use waveguides. Like for terahertz, people still use waveguides. They are better than, this is for on wafer, on chip, like your cell phone chip design. People use this type of lines called planar transmission lines because they can be integrated with your active devices. And we see these cables very often, right? They are transmission lines as well, okay? And because of those length comparable with your signal, so rigorously speaking, you have to use Maxwell equations plus the boundary conditions to solve these problems, right? To analyze the circuit components and find out how your signal is propagating and transmitting. So, yeah, people build professional softwares, like two most dominant ones. One is this HFSS, high performance, high frequency simulating systems from Ansoft. That's a major player in this area. Another one is called something called ADS, Advanced Design Systems from Agilent. Is it from Agilent?
Yeah.
Okay, yeah, Dana is using that, great. Yeah, these two are the professional, well-known professional tools, and if you talk with those engineers, okay, they know what you're talking about. You mentioned these softwares. Anyway, but if you do go back to Maxwell equation, that's a little too much because we would like to continue use our knowledge about DC circuit design, for example, right? There we handle Ohm's law, we handle KCL, KVL, right? Kirchhoff's voltage law, current law, very well, simple, easy. That's good, right? So then how do we deal with the transmission line? We said they're comparable with your wavelength. So you have the phase delay, etc. issue, right? Then the idea is to build an equivalent circuit for your transmission line. Okay? How? Then what you do, you can always put the incremental section, you cut that section of your transmission line, right? If this delta Z is very short, comparable, far smaller than your wavelength, then you can actually use your DC circuit concept. You use resistors, inductors, this is resistors, and the capacitors to describe the circuit. That simple small circuit you can, right? And then okay, yeah, in the future you will know how to find out what is R, what is L, what is C, what is G. But anyway, you have this circuit now, it's an equivalent circuit. Then you can use KVL and KCL, Kirchhoff's voltage law and current law. The voltage law says what? If you walk along a loop, closed loop, your total voltage up and down would be zero, right? Add together. That's simple. KCL means at any node, right? Your current in should equal to current out. Yeah, that's what it means. And then you put them together. That gives you a very well-known telegrapher's equation. It describes the voltage and current with a relation to these line parameters, RLCG. They are related to the transmission line itself and the media surrounding the transmission line. Okay, so when the transmission line is given, these parameters are given. Okay, then you see the voltage and the current. Now they propagate. They actually are waves. They are not like the DC stuff. DC, you apply a voltage here, automatically all the voltage, all the points on your line we assume share the same voltage, right? So you don't have time for the propagation of your voltage. But here you do need that. So it's a wave function. So your voltage now is a wave along your transmission line, and this gamma is your propagation constant. It has two components. One is the wave. When it travels, it will be attenuated, reduced because of loss. The other one is the phase propagation constant, because at different points your voltage phase, your wave phase will be different. Okay, so you have a propagation constant. You have which has two constants. One is attenuation constant. The other one is phase propagation constant. So these constants are related to the transmission line properties, R and L and C and G. Okay. Similarly, for current, you have the current wave. So now you have waves on your line. Okay. And if you observe your waves, actually you'll find out if you put two pieces of transmission lines together, and there is a parameter to describe the line called characteristic impedance. It is related to the line parameters. Okay, if these two characteristic impedance are different, you will get a reflection at this interface. So that's kind of different from DC, right? The reflection, and you will have, of course, transmission. Okay, two parts. But if these two so-called characteristic impedance values are matched, you don't have reflections. Okay? That's where we come to this something called scattering parameters, which is, I said, very special, because it looks like we found a way to describe the transmission lines, right? In terms of voltage wave, current wave, in terms of propagation constants, in terms of characteristic impedance. Then engineering, we are engineers, right? We need to solve problems. We need to design our circuit. We need to verify if our design is correct. How? You need to do measurements, right? So when you do measurements in your lab with a multimeter, for example, to measure voltage and current, what do? The first step is you want to zero that multimeter, right? You make sure before you measure, okay, you have 0 voltage, right? Then measure the voltage. That's how you do that. It turns out that in microwave, there's no such thing as a 0. It's difficult. There's no such thing, because we said even you have a micrometer, 10 micrometer, like a misplacement or gap, that will give you inductance, parasitic inductance. So that will give you a certain impedance value. For example, it's not 0. There's no such thing as 0 or perfect standard. Then what do? Then we have to find a way where we can put our hands on. Okay, we know for sure we are doing the right thing, right? So that is where the people in this area found out. They found out that, okay, actually people can design 2 transmission lines. They don't have reflections. They are matched. So they have the impedance identical. That's what they can do. They can't make a short circuit, perfect short circuit. They cannot make a perfect open circuit. No. But they can make 2 lines identical. Okay? Then that's a good starting point. As long as you can make 2 lines identical, then you can use that as a standard for the 0, the calibration process. Okay? That's the whole thing behind this approach called scattering parameters. So scattering parameter definition is based upon the incident wave, reflected wave. Okay. You take the ratios. That's what it is. So we measure scattering parameters with a special tool called a network analyzer. Okay. And before you do the measurement, you need to zero, right, to see your system if it's working properly or not. That is where you use the standard, which is you have 2 lines matched with the impedance. That's the only standard actually you need. It's a magic, right? It's a magic. You just need to know that these 2 lines are matched. Then you can rigorously characterize your system and make accurate measurements. Okay, so this piece of equipment is used to characterize all the high frequency electronics components, transistors, resistors, inductors, capacitors, and it is used to measure high frequency circuits as well, such as the gain of low noise amplifiers, okay, including power amplifiers. People use actually network analyzers. And we use network analyzers to measure noise figures, okay, everything there. And you see this, the design is pretty clever, and you can actually simultaneously apply DC to bias your transistor, and at the same time you can measure your high frequency behavior of your transistor. So today, actually all the high frequency properties of transistors are obtained with this technique, okay, this measurement. And yeah, even the IV curves they give you at high frequency, they are converted from S parameters. All right, but 2-3 years ago, I had a manager from Rody and Shorts, a company which specializes in network analyzers. And he said, hey, look, I sell equipment, like a multi-million dollars equipment set. But this type of equipment is probably the most challenging equipment to use. As an electrical engineer, as long as you can use a network analyzer proficiently, I think the other piece equipment is much easier for you to handle, okay? All right, because the main difficulty comes from this wave idea. It's a kind of a big change from the voltages, right, and the currents we are used to. Okay, and because we talked about waves, right, and there are some interesting devices you can make just by putting lines, metal wires together. Okay, for example, this is something called a quadrature hybrid. Quadrature means you have the input, right? You have two outputs. That the two outputs will be 90 degree. You will have a 90-degree phase difference. That's quadrature, right? Output. This is the quadrature hybrid. So it's just a piece of wire, right? Or metal. We use copper or gold. Then you have an input signal here. You will have 50% of the power if you design 3 dB coming out of here, and another 50% of the power coming out of here. So these two, this is we call that port. Okay, port 1 and port 4, they are isolated. They don't know each other. They don't talk to each other. This one and this one. Instead, this one will talk to here and send a signal here, and these two have 90-degree phase difference. And yes, this is another interesting one. This is called a rat race hybrid. What you have is a circle, right? It's a piece of metal. And then you connect that to 4 connectors. So your input signal, for example, coming in here. And this will be your common output. That will be, I'm sorry, you have 2 signals coming in from here. That would be your common. That would be your, where's your common? Let me see. Okay, your input 1 here, input 2 here. This is lambda over 3. That is lambda over 4. I'm sorry, this is your differential output. That is your common. So then this should be lambda over 4. That should be lambda over 4. Which means you have 2 signals coming in. Okay, that is this port. You will have a subtraction. That port you will have an addition of the 2 signals. That's how it behaves. And for this one and this one, for example, if you have 1 signal comes in from here, you will have 1 signal coming out here, 1 signal coming out here, and these 2 don't talk to each other. The similar is true with this one we talked about. So that is due to the wave propagation phenomena, okay, in your transmission line. So these are the basic circuit components in high-frequency electronics, the passive circuit modules, okay? And now you have waves, right, propagating along your transmission line, surrounded by different media. And then if you plot the phase propagation constant versus this K is the frequency, omega, okay, times C. C is the speed of light inside the volume. That's basically omega. So if you plot them together, that gives you a curve. It's called dispersion relationship, okay? And then when your signal propagating, you would like to know two things, two velocities. One is what is the phase velocity, right? How fast does the phase propagate? It's called phase velocity, which is the omega divided by beta. So basically you collect a point here and the original point. That you get a line, that the slope of this line will give you the phase velocity. Okay, and then the next question you would like to know is how fast your signal energy, your signal will propagate. Okay, that is basically the modulation, right? We know that is signal. That modulation, how fast it propagates, that's called a group velocity. Well, how do you calculate that? Then this point we just found out, right? We identified, and then you put a tangent line across that point. The slope of this tangent line gives you the group velocity. That tells you what is the frequency, the energy transmission speed. So two speeds, and you see the speeds are different at different frequencies now. Okay, that difference comes from the materials may depend upon frequency, right? At different frequencies, the materials respond differently. Or it comes from something called geometry dispersion. So depends upon how you lay out, you draw your line, how wide, how narrow. They will give you different frequency response, okay? And the interesting thing here is, you see at this point, for example, this slope is very large. That tells you the phase velocity is very high. It's higher than the speed of light. Yeah, it's completely okay. The phase velocity can be much higher than the speed of light. However, the group velocity, no. That's the energy transmission, right? We know this special relativity. You can't be faster than the speed of light, right? So at this point, what's the group velocity? 0. It does not propagate. So you can actually slow down the energy propagation in your structure significantly. And this kind of dispersion is well known in optics, right? Different frequencies, you go different paths, you have different behavior there. And this dispersion actually is very important for digital circuit designers, not only analog designers, not only RF, because if you break your computer chip, right? If you look hard, actually your computer chip can be summarized just by this very simple circuit, which where you have a driver, you have a receiver, and you have interconnect, right? This can be the inverter, that's it. Okay, break your computer chip, that's what you get. And the building block, it's like that. And yeah, the digital signals, zeros and ones, you have a broadband. And you have a lot of wires around you. That's interconnected wires. They will talk to each other. We just said they were a couple. Okay? So you could have a huge problem when your computer clock frequency is high. What's the computer clock frequency? 4 gigahertz, right? 3-4 gigahertz, right? If you buy a computer, it's very high. It's a microwave. Then you can imagine this is a headache for the computer designer like Intel, okay? Because you don't get a perfect 0 or perfect 1. No, you don't get that. You have so many. You have 1 billion transistors to be connected together, right? So one way or another. So you have so many wires for that connection. You have a lot of crosstalk issue, etc. So this is a big problem, signal integrity for the high frequency digital circuits. It's part of high frequency electronics there. Okay, that dispersion relationship, you can actually make use of that. One way is people intentionally, that's a transmission line, that's the metal. You can intentionally integrate that with something called nonlinear components. And then you can you can obtain something called solitons. Solitons means it's the waves propagate like a particle. It does not disperse. Yeah, it may shrink in terms of the amplitude. That's called an electronic soliton, okay? You can actually use that piece of wire, put some capacitors there. Yeah, if you have an inductor, you can put a nonlinear inductor there, okay? You will be able to send a pulse signal in, the pulse will propagate and keep the shape, like a bullet. Keep the shape does not deform. And it also can help you if you have a trapezoidal signal in, you can reshape the rise edge, or you can reshape the fall edge to manipulate your signal, okay? And if you derive the voltage wave, right, we said, or current wave, right? The wave propagation effect equation, it's the same as the wave here in the ocean, okay? It's kind of interesting, and last time we mentioned invisible cloak. And this is from CNN, okay? Stunning technology makes troops invisible. That's nothing but to try to build your devices or system to manipulate the dispersion, we just said, the dispersion of your material. So you can sort of make them slower or divert the waves. Okay. Yeah, if you understand that dispersion relationship we just show very well, then you can understand. This is a good starting point. Let me put it this way: for you to understand this phenomena from the circuit point of view. Okay. So there are some other transmission lines which you normally see. The first one is this. This is, I think it's from Sandia National Lab. You know, for you to build a nuclear bomb, right? You want to test if that explosion process is as you designed. How do you see what's going on inside? When you have a patient, right, coming into doctor's office, doctor wants to see this patient. Okay, does this patient have a lung problem or not? You use X-ray, right, to see. And the nuclear bomb we may I don't know, I never seen one, but I guess you have a very thick cover, right? So how do you see the explosion going on inside? You probably need a very strong X-ray machine, right? You have to. So this is actually something like that, the X-ray machine. You needed to have 10 megavolts of voltage and to generate very strong electron beams, and the electron beams will hit a target and generate very strong X-rays. The strong X-rays will penetrate and see through a large piece bulk material. Okay. Guess what? For you to generate this high voltage from 110 volts, right, on the wall to 10 megavolts, that thing, a major part is called transmission line. So you use a transmission line to do that. Okay, to manipulate the waves. Okay, that's interesting. The peak power can be huge, several terawatts, very, very high. That's on the bigger side for the transmission line. On the small side, okay, the carbon nanotube, right? Last time I mentioned, yeah, that's the UCI Burke group. He proposed the model for the high frequency methanic carbon nanotubes. He said that it's a transmission line. and he predicted this RLCG of the line parameter. We just saw RLCG. He said the L is very high. That's good. But yeah, this people are using the transmission line to describe the carbon nanotube behavior for electrical engineers. Unfortunately, we don't have experimental verification of that transmission line model yet. Yeah, if some of you can do that, that would be great. Okay, put a line there, just do the measurements, S parameter measurement, and then you could obtain the RLCG. Yeah, this inductor and capacitors. Okay. So now, we just covered the kind of special parameters we use to describe how the signal propagates, right? For example, from this amplifier to this amplifier through that transmission line, we use waves or scattering parameters. And then for you to be able to design these this system, you need to work on the circuit modules, right? Such as a low noise amplifier, gallium arsenide. And yes, you can, that is always here, I think, often the low noise amplifier. Because this is a multi-technology, yeah, you use probably ADCs, DSAs are from CMOS. Probably your low noise amplifier is from 3.5 material, like gallium arsenide I just mentioned. And you can also, more recently, you implement the whole system, this whole transceiver, in just a CMOS technique. Okay, silicon. You don't use gallium arsenide at all. And including that antenna, okay, the antenna, the big one, on silicon wafer, okay, very small. So you use zigzag lines there. Okay, for the all CMOS one, so-called CMOS RFIC, like the low noise amplifier where you need to use transistors, like inductors and capacitors. These are the capacitors. And but if you, the technology, if you cut the wafer, the chip, you look at the cross section where your transistors are on the silicon, right? The bottom. And this area is called the interconnect area. And you have a few layers called a global interconnect. What does that mean? That means you communicate across the whole chip. You have a local, which means these lines are used for the transistors to talk to their neighbors, immediate neighbors. Okay. But yeah, you can use these resources to build a whole transceiver system in CMOS there. And now you need devices, right? So these systems, the circuit components, the devices you need are the active ones and the passive ones. Passive ones you can use, yeah, you can use everything here. Active ones you probably have only, for CMOS ones, you have CMOS transistors, FETs, and you have BJTs. And you should, don't forget the diodes. You need the three, mostly. Speaking of diodes, because I don't have other data to show you, but I just would like to mention to you, so-called terahertz sources and terahertz circuits are now mostly built with diodes, Schottky diodes actually. Okay. Passive, so I just mentioned the passive components. You have what? Resistors, capacitors, inductors, right? This is a newcomer, and we don't know how to use that yet. It's called a memristor. That is here. That was a Nature paper. The observation was, okay, let me show you the next one. On the next slide, the observation was the capacitor what? Capacitor, you use that to deal with the relationship between voltage and the charge. So you collect these two with the capacitor, right? And the inductor is for magnetic flux and current. That's your inductor. Your resistor is between voltage and current, right? Resistor, Ohm's law. Now, memristor, actually they demonstrated HP by HP, is a collection between your magnetic flux and the charge. Okay, that's a brand new device. It has a lot of potential applications. Actually, I saw quite a few professors get NSF funding, for example, to study, to design circuits, how to use this new component. Anyway, yeah, here is another way to show that. It's from Nature 2008, not too long ago. Okay, so look, for you to deal with the high frequency circuits, you need just transistors. That's your active component, right? You need these passive components. And once again, this part, I don't see anybody deal with the high frequency aspect of the memristor. People are beginning to deal with the DC, low frequency behavior of this memristor. How does it behave? Okay, so it's a good opportunity to get into there. All right, so let's look at the, from the high frequency point of view, the transistors. And then how do you say, from a high frequency electronics point of view, how do you know your transistors are good or bad? You need to say, to have something like a figure of merit, right? To describe them. In general, we have two. The first one is called cutoff frequency. The second one is called a maximum oscillation frequency. What is cutoff frequency? It is unit current gain frequency. So this is basically the circuit. You have input, that's your transistor. You have output, which is current. That output current will drop when your frequency goes high. Okay, drop until it reaches 1. That frequency is called cutoff frequency. And if you don't consider the complicated physics Dr. Harrow told you, and then normally that's the gate length. If your gate length shrink by a factor of 2, your cutoff frequency will go up by a factor of 4. But if you consider some of the complicated issue, it may go up by only a factor of 2. Okay, so that's why you shrink the scaling, shrink the gap. The gate of your transistor is so important, right? You make your transistor work faster. Basically, you can think about it like you make your electrons to go through a shorter distance. Okay? That's the first cutoff frequency. Just keep that in mind. The second one is in maximum oscillation frequency, where you this time don't short circuit. You put a load and a matched input, where when you have your gain is unit power gain. So what your input power is, then you generate the same amount of output power. So that frequency point. Then I just mentioned this. So you keep shrinking the gate is very important for high speed, for cutoff frequency. Last time somebody asked me about graphene. Yes, people did build this 10 atom times 1 atom, 10 atoms transistor. That's a Nobel Prize, right? 2010. If you put this cutoff frequency and oscillating frequency maximum together for different technology, that's MOSFET. Cutoff frequency wise, it's very close to the highest indium phosphide transistors. This is the maximum oscillating frequency. Again, MOSFET is in the range of what? 300 gigahertz, 400 gigahertz? That's 2009 even. I guess people are getting better today even. Okay? So, yeah, that is a big motivation, a driver for people try to integrate the whole transceiver, the whole high frequency electronics system on single CMOS wafer. Okay? Yeah, because your speed, your figure of merit is close, is there. And if you consider silicon germanium BJT, that is often considered CMOS as well. And it is very close to the 3.5 material. Okay, and in terms of high frequency digital circuit design, right, high speed, there you talk about propagation delay. What does that mean? That means you have a driver, you have a receiver, identical, fan out of one, and your input signal, and you see your output signal. How much time does it take for your input to propagate to the output? It's on the order of 1 picosecond. 1 picosecond is very fast. Okay? All right. Now we move on to look at the passive devices, because I said we need three different types of passive devices. You need a resistor, you need a capacitor, you need an inductor, right? And the resource you have is here. You have the active, where you build transistors, air and laser. You have the passive region. You have metal wires, basically. Yeah, people use both to, these are the pictures of the interconnects, the metal wires you can use. And the people use, okay, there's another interesting effect. When you have two wires, they are too close, so close to each other, you have, first of all, for high frequency, you have the skin effect. You probably heard about that, right? Which means your high frequency energy will not be propagated through the whole wire. Instead, only the surface area will propagate the energy, and how deep it is related to your frequency. Secondly, you have something called a proximity effect. So if you have two wires close together, they will interact with each other. So the current distribution, instead of uniform, they will be something like this. So that was part of the problem for this so-called signal integrity there. Okay, now look at the transistors. You can use the polysilicon, you can use the active or doped silicon area for well transistor resistors or poly resistors. That's similar to the lower frequency operation, but for high frequency, the problem is this: okay, you get a resistor, it's not a resistor. Okay, you have other components. For example, you have parasitic capacitance. Okay, the capacitance could kill you at high frequency, because instead of have a resistor, to go from this terminal to this terminal, halfway or somewhere you will get short circuit at high frequency, because high frequency, the impedance here is very small. Okay. Then imagine when you use some technology, you have to be aware of this, right? For how high I can go. And then how do I modify my design? This is called layout, right? That's the actual resistor for how high a frequency I can operate. Yeah. Similarly, capacitor, you use two electrodes to store charge. That's it. Then the question is, okay, if I have this capacitor, then what is my resistance value? How high I can go? Because, for example, your bottom plate or one electrode, well, you will always have parasitic capacitance to the ground. So at a very high frequency, this one could short circuit your output. So how high can you go? Then what kind of geometrical arrangement you can make? So you can make it go higher. A third type is inductor. And this is the kind of inductor, if you look on a microscope, people actually built on wafer. And this is called spiral inductors. It's similar to these discrete components. Once again, the question is how high you can go, the frequency, operating frequency. That's always the limitation. And then right now for on-chip one, for computer technology ones, you can generate this inductance value on the order of 10 nanohenry. Not very large, okay? 10 nanohenry or 20 nanohenry. What does that mean? That means equivalent to a 1 centimeter long wire, right? And the frequency-wise goes up to like 10 gigahertz, which your cell phone works at about 1 gigahertz, right? 2 gigahertz. So that's where we are. If you come up with a new design which can make the inductors work up to, let's say, 20 gigahertz with a much higher inductance values, you can be very rich because we don't know how to build such inductors yet. People have tried all kinds of potential techniques, such as put magnetic materials in. Okay. With these components, yes, you can build the circuit modules, and you put the circuit modules together to build the systems, to build the transceivers. And yes, you can, if you use CMOS circuit only, you can integrate the digital part, and analog part together. Okay, I think this is my last slide. So from that, you can build a very inexpensive consumer products and to help change the world again, right? So this is my last slide. Thank you for your attention. Do you have a question?
I have a group versus phase velocity question for you.
Okay.
So group velocity really is the transmission velocity of the energy, and it can't exceed the speed of light.
Yes.
When we talk about speed of light, really we're talking about group velocity of a wave.
Mm-hmm.
So is not the group velocity of any electromagnetic wave in a vacuum actually c? Is that what we mean by speed of light in a vacuum? Isn't it the group velocity?
Yes.
And it only diminishes from that when it's propagating through some other medium
Mm-hmm.
with a different refractive index.
Yes, but when we talk about the speed of light in vacuum, like when we talk about that, we're automatically assuming you are propagating in something called TM mode, transverse electric and magnetic mode. So in that case, your group velocity and your phase velocity are identical. So you don't need to differentiate these two. What happens is when you have a transmission line, you have a metal wire there, then these two are not identical. When they are identical, you actually have a straight line which goes from here, like this straight line. So there you have the same slope. Mm-hmm. That's good. And actually, I had students ask me to draw a picture, show me how can your group phase velocity be higher than the speed of light. Okay, I should have that picture here. People often use the water waves when the water waves approach a seashore. They say if you see that water wave propagation, I never got it, okay? I just mentioned that to you so you can figure out why the phase velocity can be faster than the group velocity, energy velocity there, be very fast. I didn't get that analogy there, but I did have a picture where you can see if you go into detail like two parallel plate, you put electromagnetic waves in, then you know how to calculate the phase velocity and the group velocity there. Then you see that the phase velocity is indeed much higher than you can be much higher than the speed of light. Okay? Yep. And as I said, if you manipulate, you can put metals on your let's say PCB board. You can put metals at different places to change the environment of your signal transmission line. Then you can change this omega beta relationship. You can make it a very narrow band, so only that frequency range of signal in that frequency range can go through your transmission line. You can change these things. You can engineer this relationship. And that, as I said, that's what they do in terms of developing so-called metamaterial, so-called invisible cloak. That's what they do. They put something in to change the relationship. So for certain frequency range, then they only go in certain way, okay? Or they don't go through. They will be completely reflected back. So it's kind of interesting. I thought I had a slide where I showed you the guy who started the whole thing. Looks like I don't. Started the invisible cloak. He was awarded this Cavani $1 million award this year in California for this invisible cloak. For some reason, I don't have that slide. And yeah, actually in my group, we are working on how to manipulate the so-called dispersion relationship for biomedical and biochemical sensing purpose, right? And you can, because you can make the wave much travel slower. The other day I mentioned this way. Yeah, you can intentionally make the wave very slow, so that the wave can interact with your material for a very long period of time, right? Then theoretically you can increase your sensitivity because the interaction is very long. And I think 10 years ago or 12 years ago, I read a paper by Princeton University physics department. They were developing some technique to slow down the light to about 10 meters per second, the speed, to a few meters per second, instead of how many meters? 300 milli?
3 times.
Yeah, 10 to the power of 8. Yeah, you can slow down the waves. Okay? All right. And one more thing I can mention to you is this. In high-frequency electronics, or in the filter is a very important component, or circuit module. You depends on how you look at that. Where's circuit? Okay, these are the filters Filters means you let certain frequency signal pass through or reject certain frequency signal, right? So that when I'm talking to Matthew like over the phone, we don't hear what Dr. Harrow is talking with somebody else, right? That's because we need that filter. Otherwise, it's a mess. Okay, the filters design, you more or less is related to, it is related to signal propagation, high frequency. And this, very often you start from the this gamma. You control the gamma. In other words, you control the dispersion relationship I just mentioned. Okay, the gamma has the beta, right? You have the beta, you have the omega, you control that. Okay. All right. Is it too technical, guys? Maybe it's too technical, right? Okay, that's what we do in high frequency electronics, what people do. And I do believe high frequency electronics will be more and more used, right? Because wireless communication control in the smart home, everything, we need that, right? That's it, right?
Any other questions? Thank our speakers.
Thank you. Okay, I'm going to shut down now.